We did the marble drop lab in class today, and just a reminder, this is what it looks like. We dropped the marble and the buggy caught it. And we all did really well in the calculations, and we were definitely successful. What I want to do now is show how this lab transitions into the topic of two-dimensional motions. We have two scenarios. One is I've just taken the buggy marble lab that we did in class and turned it into a physics problem. And the second thing that I've done is set up our first two-dimensional motion problem. And the whole premise here that we were talking about is simply that in this scenario, this marble, whether it's launched horizontally or dropped, lands at the same time. Like if you look at its journey, it in each stage, whether it's moving horizontally or being simply dropped, both marbles are falling at the same rate and undergo the same acceleration of 9.81 meters per second squared. Okay, that all sounds very good and nice. Let's actually apply this practically to the physics that we're going to be looking at in the next unit. So let's start with the problem that we're familiar with. So we have a marble, it's going to fall, right? We have a buggy right here, right? And it's going to roll up and catch it. And we'll say that this is x and this is x naught, and that x naught is 0, and that x final is unknown. That's actually what we're trying to solve for. And we don't know the time. We do know that the speed of the buggy is 0.4 meters per second. And we don't know that the time that it's going to be traveling for. In the meantime, we have this marble that's dropped, so we know that its displacement s is 2. We know that it starts from rest. And you know what? Just to be safe, I think what I'm going to do is I'm going to use different colors for the marble. So I'll actually color the marble in this orange color. And what we're going to say is that u of the marble is 0. V is unknown. We know that S is going to be 2 meters. And we don't know the time it takes to fall. And we do know that its acceleration, because it's accelerating due to gravity, is going to be 9.81 meters per second squared. So this is what everybody in class did. First, they looked at the marble and they said, okay, if we apply suvat to the marble, S is 1/2 AT squared plus U times T. And so we say that 2 equals 1/2 times 9.81 times T squared plus 0 times T. And, you know, let's just be clear, it's actually 2.00 meters since we had a meter stick. And so we're going to get 4.00 over 9.81 equals T squared. And we can actually get the square root of both sides to get the time that it takes the marble to fall. When we work out that number, we will, in fact, end up getting something around 0.639. So 0.639 seconds is the time. And as we work with this, we can now look at what's happening with the car. So for the car, what we concluded is that it needs to be rolled back a certain distance that we're going to calculate now. So the car distance, basically we're going to say x equals v naught t plus x naught. And our goal is to calculate this distance the car needs to be rolled back by in order to roll up and catch the marble. So we're going to say x equals, we have 0.4 for the car, and we used the 0.639 for the marble. And that's plus x naught, which is 0. And so when we actually worked out our number, what we ended up getting was a distance of 0.255 meters. What everybody in the class actually did was they rounded, or they converted their answer to centimeters. So our answer would be 25.5 centimeters, like that. So that's what we did with the Buggy Lab. Now, here's where things get interesting, and this is where we're going to take this challenge problem that we did and extend it into the world of physics, of objects moving in two different directions. So specifically, let's take a slightly different problem. So I'm going to call this horizontal position on the ground x naught. And I've labeled this v naught x as 0.4. I want to be clear though, in the vertical direction, u equals 0, v is unknown, a is 9.81 meters per second squared, and t is unknown. And let's just be clear that s, the displacement, vertically speaking, is 2. So this marble is doing two things at once. It's falling and it's moving horizontally. So this is the big secret to these problems. And I'm typing this, but I want you to write this in your notes. So the horizontal and vertical motion are independent. Only time, okay, they only have time in common. And we're going to actually apply this strange abstract idea very practically to this problem right here. So here's what this means. Vertically, we're going to look at, instead of the marble, we're going to call it falling. And here's the idea. Setting up SUVOT, we're going to get the time to fall. Okay. Let's get the time to fall using SUVOT. S is 2, U is 0. Be really careful. It's very tempting to say, no, wait, it's 0.4. Let's be clear, that's in the horizontal direction. What we said, horizontal and vertical motion are independent. What that literally means is that any value for x is an x value, any value for y is a y value, and we treat them independently. So in other words, the buggy problem with the marble is in fact identical in so many ways to the marble being launched horizontally. We don't know v, a is 9.81, and t is unknown. So let's get the time to fall. So we have s equals 1/2 a t squared plus u times t. And that's 2 equals 1/2 times 9.81 times t squared plus 0 times t. So we have 4.00 divided by 9.81 under a square root. I did simplify a little bit of algebra there. And so I'm going to get that t equals, once again, similar square root. In fact, it's identical to what we did before. So we're still getting 0.639. Now that part's not surprising. Now let's look at what the marble does horizontally. So now let's talk about the horizontal motion. And we're going to set it up like this. So we're going to say x equals v naught t plus x naught. And let's remember, our goal is to calculate this separation distance from the bottom of the table edge here to the distance where the marble actually lands. So that's going to be x equals 0.4 times this time that we had before from above, 0.639, because the time spent falling is exactly the time spent traveling horizontally, plus 0. And so we're going to get that the marble lands a distance of 0.255 meters from the edge of the table. Or, if you prefer, 25.5 centimeters. So the whole point of this homework problem was to sell you on the idea that two-dimensional motion can be thought of as combined one-dimensional motion in two different directions. Let me say this another way, okay? The marble rolling with a horizontal speed off the edge of the table behaves like a combination, behaves like the buggy in the x direction and the marble in the y direction. And I'm going to say, and the lab marble. So the problem marble, so the marble in this problem is what I'll say. Rolling with a horizontal speed off the edge of the table behaves like the buggy in the lab buggy in the x direction and the lab marble in the y direction. That's the whole point. This one marble, its combined motion is actually made up of two separate motions that share time in common. So that's kind of our first topic that we're introducing. And when I see you on Friday, we're going to really dig in, and I'm going to give you a lot of practice doing problems like this so that you feel totally comfortable. This video, I'm calling it a homework. It's honestly kind of a lecture and an introduction to what we're going to be doing Friday.